So if your first step is correct, so actually the follows are quite straightforward. So our augment cost function is given by, so I just copy the equations in the Vx df in relation to the final state plus the integration from t0 to tf. So we just separate the algebra part and the differential part. Remember that. So we have the lambda 1 Vx plus lambda 2 Vy plus lambda 3 cosine u plus lambda 4 sine u. So this part are the algebra part. So this plus the differential part, So it's a minus lambda 1 x dot plus lambda 2 y dot plus lambda 3 vx dot plus lambda 4 vy dot. dt. So here we actually almost arrive at the solutions. So at here, remember this part is actually our Lagrange. This part is actually our Hamiltonian. This part is our Hamiltonian. This one is defined by the L plus the lambda f, the small f, lambda small f. And for this part, it's just the algebra part. Remember, in the derivation of the equations, when we perturb this differential part, we need the integration by path equations. To solve this. You remember that, right? We apply the integration by paths so that we don't need to perturb the derivatives. We only need to perturb the lambda. So in the derivation of equations, next we set all the perturbations to be 0. Then we arrive at the Euler Lagrange equations. But here, I will not derive all the equations again. So we just use the Euler Lagrange equations. So from these equations, we know the H is Hamiltonian. This Hamiltonian is given by this lambda 1 Vx plus lambda 2 Vy plus lambda 3 cosine u plus lambda 4 sine u. So next, we can use our Euler Lagrange equations. So our first set of equation, remember our first set of equation is dh du equal to 0. So now let's check what is dh du. And here, because we only got a single input, so it's a scalar input, so I just draw the vector notation because this u is a scalar. So we have our h at here. So what is dh du? So the first one is lambda 1 Vx. It's independent. It has nothing to do with u. So this part will be 0. Then this part, the lambda 3, is a constant in terms of u. So the cosine u will become minus sine u. So this becomes minus lambda 3 sine u plus this lambda 4 cosine u. So this equal to 0. Equal to 0. So we have lambda 3 sine u equal to lambda 4 cosine u. So we have this tendency u equal to lambda 4 divided by lambda 3. So from here, we can derive the optimal control. So this optimal control equal to arc tendency lambda 4 divided by lambda 3. So these are the equations of the optimal control. But so far, the optimal control is in terms of the Lagrange multiplier. And in the general case, it's also related to the state vector. In the general case, it's also a function of state vector. So how to determine this Lagrange multiplier and the state vector? We have another two sets of differential equations. Remember, we can use the shooting method to solve the differential equation. To solve the differential equation, that will give us the values for the Lagrange multiplier and the state vector. So from that, you can derive your final optimal control. So the second set of equation, the Euler Lagrange equation, is given by, remember, our lambda dot equal to minus dh dx. And here we got 4 lambda. So this lambda, because we have 4 equations, is given by lambda 1, lambda 2, lambda 3, lambda 4. So I put the transpose so that this one will be a column vector. So this x, this state vector is actually defined by the location of your vehicle, this x, y, and the velocity of your vehicle. So from this definition and this equation for the Lagrange multiplier, we know the lambda 1 dot equal to minus dh dx. So remember, this x is different from this x at here. So this x is the state vector. This x is the state vector defined at here. And this x is just the coordinate, the x coordinate of the vehicle. It's one of the components here. So how to evaluate this dh dx? So we check the equation for the h. So the h is a function of vx, vy, and the u. So it has nothing to do with the location of the vehicle. So this one equal to 0. If the lambda 1 dot, we know the lambda 1 is a time function. If a derivative of a function equal to 0, that means this lambda 1 is actually a constant. It's actually a constant. So assume we have this constant to be C1, with the constant C1. So the lambda 2 dot equal to minus dh dy. So again, the h has nothing to do with y. So the dh dy also equal to 0. So from this one, we can derive the lambda 2 is also a constant. So assume we have this constant to be C2. So the lambda 3 dot equal to minus dh dvx, dh dvx. So we have the h at here. So the dh dvx will give us a lambda 1. So only one vx at here. We got a lambda 1. So this becomes minus lambda 1. But from here we know that lambda 1 is a constant. Lambda 1 is a constant. So this lambda 3 in terms of time equal to, so it must be a linear function of time, because this lambda 1 is a constant. So the gradient is a constant, is a linear function, is a line. So this is given by minus lambda 1 multiplied by t plus a constant. So assume we define another constant for this one. So lambda 1 equal to C1 with C1 t plus, we define another constant for this one. So it's got C3. Lambda 4 dot equal to minus dh dvy. So the dh dvy we know just give us lambda 2. Just give us a lambda 2. So this equal to minus lambda 2. So similarly, we may derive this lambda 4 t equal to minus lambda 2 t plus another constant. So we assume we define this lambda 2 equal to C2, so it's C2 t plus, we define another constant for this one, C plus C4. So now we have the equations for all the Lagrange multiplier. Now we can recheck the control input. So our optimal control input, so this U star, this UT star is given by arctangency lambda 4 divided by lambda 3. So it's become arctangency. So the lambda 4 given by minus C2t plus C4 divided by minus C1t plus C3. So where all the 3i are constants. So these constants actually depend on the initial condition. So remember, if we use the shooting method, we can determine the value for this constant, because so far we have not used the initial condition and the final condition. So this is the first example that we want to discuss. So from here, it's quite important to construct the correct Hamiltonian. Once you construct the correct Hamiltonian, you use the Euler-Lagrange equation that will give you the solutions. So So we have one set of algebra equation and two sets of differential equation. So this one is the first set of differential equation for lambda. And here we got another set of differential equation for x. So if you solve these two sets of differential equation by using the initial condition, so you can determine the unique value for the agreed multipliers. So here we are not using the boundary conditions, so we just get these constants, but the values are unknown so far. So we will discuss another example. So this second example is more straightforward to understand. So you want to minimize cost function. So it's given by this t equal to 0 to 2 seconds, the u square dt subject to x dot equal to 3x plus u. So the initial condition and the final condition are the x0 and x2 are free. So in this equation is quite standard format. We have a standard differential, we have a standard cost function, and we have a standard differential equation for the dynamics of the system. So this equation, the cost function is quite similar to our example that we discussed before. You still remember our one-dimensional path planning problem. I want to optimize the control energy. So here you can understand that. So this one is actually represent the control energy of your input from the T0 to Tf. So here you can see we try to minimize control energy. And this one is just the dynamics of the system, dynamics of your vehicle. And it's more interesting to check the initial condition and final condition. So the initial condition and the final condition is the initial position of the vehicle at t equal to 0 and the final condition of the vehicle at t equal to 2 are free. So when you check this problem, you find that you got a vehicle at here subject to this dynamics. So now you want to minimize control energy. But however, your initial position and your final position of the vehicle are free. So there are no requirements on the initial location and final location of the vehicle. So in that case, what will be the solution to the problem? So in that case, the solution will be 0. So if you don't apply any control input, if you don't apply any control energy, you will still satisfy this final condition. So for example, if you have your x2 equal to x0 equal to any constant. So eventually the required control energy is 0. So it's important to fully understand the physics behind the problem. So that will be very helpful for you to solve the equations. So don't treat the problem as simple mathematics. Don't directly go to the mathematics and all the equations. Put a lot of equations, eventually get the solution. So try to fully understand the question and make some analysis on the questions. So sometimes it will be very helpful. So from our intuitive understanding, we know actually this U star equal to 0. U star equal to 0 because the initial condition and the final condition are free. So there are nothing to be satisfied. So in this case, definitely we got this J star equal to 0. So the no energy required in this control. So this is the first method to solve this problem. So if you check the previous exam papers, you will find similar question as well. So there are 20 marks for the question. So if you just put the solution and explain the reasons, you will get 20 marks. So secondly, I will provide a standard solution to this problem. So you will see the standard solution is a bit challenging for you. So although the equations are easy to establish, but because we get the differential equations, so to solve the differential equation requires some mathematical knowledge. So our second solution is just a standard solution. Remember our Hamiltonian can be constructed by H equal to L plus lambda F. So this L equal to U square plus we only got one different equation, so we only require one lambda multiplied by F. So this F is an elder part, 3x plus U. So you should fully understand the reasons why we only have the F at here, but not the x dot. So remember what we derived just now. So we actually augment the cost function with this F minus x dot. But the x dot has been dealt with separately. So we just use this F at here. So once we construct the H, we can use the necessary condition, also the Euler Lagrange equations. So the first one is dH du. This must be equal to 0. So the dH du equal to 2u plus this 3x. This will be 0. So this plus lambda. This equal to 0. So this gives us the optimal control input is U star. So this U star equal to minus a half lambda. But so far this lambda is unknown. So in order to determine this lambda, we need another equation. So it's lambda dot equal to minus dH dx. So dh dx equal to, so this u squared plus equal to 0, this u equal to 0. So this equal to minus 3 lambda. So now we got this differential equation. So we have this differential equation. So the lambda dot equal to minus 3 lambda. So typically the differential equation is not easy to solve. And actually the solution to the general differential equation are not required in this course because it requires quite a lot of mathematical knowledge. So here I just give you the solution. So this one is a very simple question. So actually you can solve it by hand. So you can check the website. The derivation are not wrong. But when you solve this, you will get this equation like this. So this lambda t. So it's a time function. This lambda t equal to lambda 0 is the initial value for the lambda multiplied by e minus 3t. So we have this 3 at here because we have this 3. We have this 3 at here. So in this function, we notice that we got this initial condition for lambda. Initial condition for lambda. So to determine this initial condition for lambda, we can use our boundary conditions. In our boundary condition, because we have our x0 is free. X0 is free, so this lambda 0 must be equal to 0. Remember our boundary condition. So if the lambda 0 equal to 0, so we have our lambda t equal to this lambda 0 multiplied by e to minus 3t. So this lambda 0 equal to 0. So we know this one equal to 0. So we have this u star t equal to half lambda t. So this must be equal to 0. So we actually get the same solutions. So from these two methods, you know, if you can fully understand the problem and use the first technique, it's much easier for you to get the 20 marks. But however, if you go through the second method, you come to the different equation. But if you cannot solve this different equation, so you can only get half of the marks. Okay, so let's have a break for 5 minutes.